we'll talk about circular motion and relative motion. So we're going to be applying a lot of vectors. So if you didn't understand vectors from previous chapter, this is going to be slightly difficult. Okay? So let's talk about trajectories and two-dimensional motion. So if we were to look at an object moving in a plane, let's say we see a bug moving like this, okay? This dashed line right here is the actual path that bug walks, okay? So this delta L right here, this delta L is the path length, okay? This position vector, right, R1 represents the position 1 of this bug. You can also represent that R1 vector as your initial position. Or you could simply say initial position like so instead of 1. Because, I mean, you could start here, I guess, as initial, or here. So there could be many different positions, but we decide to start from here, okay? And then we watch this bug walking along this path, and then we take a look at the second position, all right? This is position 2, or sometimes we can represent that as the final position. Okay, final position. This is the displacement vector of change in position. So here, your change in position, here is your R final minus the R initial. This is known as the displacement vector. So change in position vector is simply final position vector minus the initial position vector. Okay? Or simply RF plus negative RI. Okay? So if we were to say RF, if we were to redraw this, RF plus negative RI, and we get ourselves change in position, which is exactly the same as that. Okay? I'm not going to redraw that here, so you should be able to see that. So RF minus RI, or plus the negative RI, and this is RF minus RI, which is exactly same as that. All right? So this actual path is known as the trajectory. All right? Don't forget, this is not a position versus time graph. This is position versus position graph. Position in the x-axis versus position in the y-axis. Time is implicitly defined with inside these position functions of x and y in a parametric equation. Okay? So if I were to find the position of my first position here at P1, I would use T1 to figure out what the position is in the x direction and what the position is in the y direction at T1 for both of those dimensions. That would define the position one in x, y position versus position function graph. Okay? Later on, we will see this bug will have instantaneous velocity vector that is tangential to the trajectory. So this is v1 and this is v2. Okay? So time is represented implicitly, right, with multiple r vectors. Okay? So if you want, like, you could literally break this up into individual time, like, t, like t1, t2, t3, t4, t5, t6, and all these times will pretty much produce different position functions at those times. Okay, it will just fan out at infinitesimally small time periods. Okay. So in the limit, as delta t approaches 0, so instead of taking a really long time to look at these two time frames, if we were to take a look at very, very small time frame, like delta t approaches 0, right? Okay. You can see, okay, the displacement vector becomes the tangent to the trajectory of the curve. Okay? Because if you were to think about, like, as you bring this closer and closer and closer and closer together, your delta r, as it approaches 0, instead of being a secant line between the two position vectors, the two position vectors are right next to each other. Then, instead of becoming a secant line, when your delta r approaches 0, that secant line turns into a tangent line that goes through just that one point. That's calculus, right? That's basically the derivative. Okay? So this delta r, okay, as delta t approaches to 0, right, it becomes tangent line to the trajectory of the curve. So if we were to just look at this, where the 2 points are, separated by greater amount of delta t, right? That delta t, let's say, is not approaching 0, then this delta r over delta t is our average velocity. Okay? Now we should know that, right? So remember when you are doing your summer assignment, your v is equal to delta x over delta t, right? Well, when we're doing in 2 dimensions, instead of delta x, it becomes delta r. Okay? So as delta t, right, approaches to 0, right, then instead of being an average velocity, it becomes an instantaneous velocity at that time t. Okay? So instead of being an average velocity of delta r over delta t, now it becomes v, where v is the derivative of your position function. Okay? So here, in this case, this is the average velocity. Right? From t initial to t final. This becomes instantaneous velocity at that time t. Okay? At that instant. Maybe I should put a comma there. All right. So it's important to understand that velocity vector will always be tangential. This is instantaneous velocity now. It's going to be tangential to the trajectory. Okay? Tangential to the trajectory. Now, velocity has two components, two things. It has magnitude and it also has direction. So you can change velocity by either changing the magnitude of the velocity, or you could keep the magnitude of the velocity the same and just change the direction, or you can change both simultaneously. So whenever there's change in velocity, there's definitely an acceleration. Therefore, you can have change in velocity even if you are going at a constant speed when you are changing the direction of the velocity. All right? So maybe we should write that down even. So even if speed is constant, right? Velocity can change, right? If the direction changes. Okay? So you can change velocity two different ways. Either change the magnitude of the velocity, which is the speed, and keep the direction the same, or you could keep the speed, the magnitude the same, and change the direction, and you can change velocity. And, or you could do both. Simultaneously speed up as you change direction, or slow down as you change direction, and you're doing it both ways. All right? So if there is a change in velocity, right? So here, if there is change in velocity, there must be, right, acceleration. There's no negotiation on this. Whether you change the velocity by changing direction or whether you change the velocity by changing speed, Whenever there's change in velocity, there's no negotiation about this. There has to be an acceleration going on. Louder? What's the matter? I'm frozen? Okay. Hold on. I'm going to try to pause syncing for the OneDrive. I think that's stealing a lot of my bandwidth. Is it better? Hello? Can you guys hear me? Can you guys hear me? Hello? Can you guys hear me? Hello? Yeah. It's a take home. Yeah, you're supposed to have quiz today, but it's a take home, so I'm going to give it to you after the lecture. I told you that. I'm going to give you the quiz after the lecture today, so hopefully, can you guys hear me okay? Yeah. Yeah, I think the OneDrive was trying to sync and it was stealing all my bandwidth, and I think that's why it's frozen. Are you guys okay up to here? Yeah? Or no? Oh, that's not good. Is that okay now? Can you guys see that? Are you okay up to here? So even if the speed is constant, velocity can change when you change direction of the velocity, right? Right? So if there is change in velocity, there must be acceleration. There's no negotiation on that, right? And because acceleration, right, acceleration is change in v over change in t, right? Delta v here is equal to vf minus vi. So what does that mean? So here's your vi, here's your vf. So vf minus vi and here is your delta v. Okay. This delta v has exact same direction as your acceleration. Okay? Therefore, right, the delta v vector and the acceleration vector right, always point in the same direction. Now the magnitude may be different depending on what the delta t is, right? If delta t is greater than 1, obviously the magnitude of A is going to be less than delta V. And if the magnitude of, well, if delta t is less than 1, your magnitude of A will be greater than delta V. But they'll be pointing in the same direction as each other. Okay? So here, when I see these two final velocity and initial velocity, there's definitely change in there. And if I were to look at the average of these two, my acceleration vector will be pointing in this direction, which is same as this, delta V. Okay? So if this is my velocity vector, which is this way, right? A tangential, A centripetal, total A, like so. We'll talk about this more in detail when we talk about circular motion. All right, so here's a concept example, and once I do this, I will end the lecture. So draw a position vector for points A, B, and C. So that's easy. All you have to do is draw a position vector. Now this is the trajectory right here, right? So position vector for A is from the origin to that position right there is my R1, right? Or RA, I should say. And then this would be RB, RBs, right? This would be RB. And then this will be RC. All right. Now particles moving at a constant speed of, let's say, 10 meters or 10 centimeters per second. All right. So draw in displacement vector for A to C. For A to C, the displacement vector is RC minus RA. So this would be the displacement vector, or simply this. This is same vector. So this is, right, displacement vector delta R from A to C. All right? And then off to the side, draw the change in velocity vector for A and C. So A vector right here, A position will have, I would say, tangential to my trajectory. It looks like it's right on the. So I'm going to say it is tangential to my A position. I'll say this is my A vector, and it has to be 10 centimeters per second, so it's going to be constant speed. And here, my C vector is this. So my velocity vector at C and my velocity vector at A, right? So here, if I were to redraw this, here's my VC minus VA. So I will be going in the negative direction. Don't forget, it's the same magnitude because it's going at a constant speed. So here is my delta V. And my acceleration vector, it's going to be in the same direction, but we don't know the actual magnitude of that, right? Because we don't know the delta t. So this is my acceleration vector, which is delta v over delta t, right? Which is different length. Then delta v, right? But we'll have same direction. As delta v. All right. Done.
You're just like freehanding what looks like the tangent lines, right? There's no
Correct.
measuring.
Yeah, I'm just freehanding it. I'm just eyeballing it. All right. So we'll stop there for today. Work on the dot product, cross product, and then upload it by tomorrow night, midnight. So you have more than enough time to work on that. Fair? Yes?
Thank you.
All right. All right. Have a nice day. I'll try to post this. I will try to post this